Hello friends, welcome to my channel. Let's have a look at a newly appeared problem. Problem 2436, minimum split into subarrays with GCD greater than 1. In this video, we're going to share a method based on linear scan and check GCD. First, I'll read through the statement to digest the problem requirement, and then we do a simple analysis, and finally we share the code. So we are given an array called nums consisting of positive integers. So we try to split the array into one or more disjoint subarrays such that each element of the array belongs to exactly one subarray. In other words, we partition the array into a number of subarrays. And secondly, the GCD of the elements of each subarray is strictly greater than 1. So we want to find the minimum number of subarrays that can be obtained after the split. So this minimum requirement actually requires us to split or partition the array and make each of the subarray as large as possible with the constraint the GCD is greater than 1. So the GCD is the greatest common divisor of two integers. So let's look at the two examples. So example 2 actually is simple because here all the numbers are even numbers. At least 2 is a common factor. So we just need to use the whole array as a partition. So in the first example, so actually the two subarrays we can get is this one, the first three elements, and the last two elements. The reason is that you can see 12 and 6 has greatest common divisor, 6, and 6 and 3 has greatest common divisor, 3, but 3 and 14 will actually have GCD 1. In other words, they are mutually prime. So then in this case, so we are going to have 12, 6, and 3, the largest possible one, satisfying the problem requirement. And then the last one for sure can be put in together. The reason is that they are both even. So 2 is actually a common divisor. Or actually, it's also the greatest common divisor for this two number. So that's the two examples. So the constraints on this problem are the following. First, the length of this array nums is bounded below by 1. In other words, it's not null, and bounded above by 2000. So this is the actually defines the problem size. The second constraint is on the range of elements in the list, which is greater than or equal to 2 and less than or equal to 10 to the power 9. So with that said, so actually we can analyze the problem. So our method will be a simple linear scan. So we are going to check the GCDs when we doing the scan. So the prerequisite for this problem is that we need to know how to compute the GCD of two non-negative integers. So in this problem, we are concerning about positive integers. Actually, in general, we should know how to compute GCD of two integers, which can be negative, right? So for this, actually, for the computation of GCD, we could either use the math GCD function directly. So this is much cheaper. Or we can make our own implementation. So here we shall do our own implementation for practice purpose. So the procedure to address this problem can be the following. First, we're going to initialize a result. This is a variable to count the number of subarrays. And we are going to set the previous GCD to be num0, the first element. Then we are going to linearly iterate over the remaining numbers of the list. So in the process, we compute the GCD of the previous GCD and the current number, right? So there are two cases. First, if we get the GCD of the previous GCD and the current number, that is 1, then in this case, the current number shouldn't be in the previous subarray. In other words, the current number should be in the new subarray. So in this case, we are going to increment the result by 1 and reset the pre-GCD to be nums I. In other words, this nums I is in the incremented subarray, right, counting. So in other case, if the GCD of the previous GCD and nums I is greater than 1, so it means that we can add nums I to the previous subarray. So in this case, we just update the previous GCD to be the GCD of the previous GCD and nums I, and continue the linear scan. So we do not open a new subarray. So this is the procedure. So here, before we write the code, it might be good or helpful to do a walkthrough. For example, this is example 1, right? The pre-GCD is the first number 12, and the result is 1, meaning that 1 is counting the array, including the number 12, right? So when I equals 1, so GCD of 12 and 6 is 6. It's larger than 1. So we set previous GCD to be the current 6. And then we continue. So we look at 3 for index 2. So GCD of the previous GCD, that is 6, and 3. So it's 3. 3 is greater than 1. So we continue, and we set the previous GCD to be 3. And next, for index 3, so we have the GCD of 3 and 14. So their GCD is 1. So we are going to start a new subarray from the element 14. Then the count should be incremented by 1, that is 2. And the previous GCD will be reset to be the current number, nums 3, that is 14. And then for I equals 4, so GCD of 14 and 8 is 2. So we set the pre-GCD to be 2, and the result still remains 2. And then this is also the end of this list. So we return the final stage of the result, that is 2. So that's a walkthrough for example 1. So with that done, let's look at the code. The code will be a very straightforward translation of the procedure. But for practice purpose, I'm going to first implement a GCD function. So the GCD, I'm going to make it a method, right? So or we can put it in the nested function. But here, to isolate the procedure, so we write it as a method. So self, and then we're going to give 2 numbers. So here I'm going to assume n and m are non-negative. So actually, if they are negative, so we just need to use their absolute values. So this is actually a basic treatment but for this problem, so this will be sufficient. So first, let's treat some special cases. So if n equals 0, so we're going to return m, right? If m equals 0, so we're going to return n. So this is the trivial. So next, so we're going to check if n is less than m. So I want n is the larger one. So we're going to do some switch. So and then we know that n is no less than m. So then first we're going to check if n is a multiple of m. So in this case, we're going to return m. Otherwise, so we are going to do a integer division, def mode. So we are going to divide n by m. Then we know that the GCD of n and m equals the GCD of m and r. So then we're going to return self GCD m and r. So in other words, we are using a recursion for this method. So for a check, so actually we can print the self GCD. So what's the GCD of 12 and 6? So it should be 6, right? So 6, and let's see the with 5 should be the 1, right? We get 1. That's it. So now with that done, so let's look at the problem logic here. So first, I'm going to get the length of the nums array just for some convenience. And then we're going to set the result to be 1, and the previous GCD will be nums 0, right? What we are going to do is to iterate. So for I in range 1 to n, then we're going to compute the current GCD. So self GCD of the previous GCD and the current numbers, so nums I. So we're going to check if common. I've compared the comment with respect to 1. So if this 1, in other words, so if we add this nums I to a previous subarray, so it will have a GCD 1. So that's not good. So we're going to increment the result by 1. In other words, we need to hold the current number using a new subarray. So in this case, we are going to set the pre to be nums I. Alright, so this is the if condition. Else, if comment is greater than 1, so nothing special, just update the pre to be common. Then finally, we return the result state. So that's a full solution format for this problem. Yeah, if we consider to use the GCD function of the math library in Python, so this just reduce the length a lot. But we choose to do this for practice. So with that said, let's do a check. So common. So let's see this COMMON. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. I guess for this problem, that's about it. So in this video, we practiced the implementation of GCD, and also we do a linear scan to address the problem logic. So with that said, I guess that's about it for this video. Thank you.